Hello class, today we'll be going over Module 8 homework, and Module 8 is on logarithmic functions, and logarithmic functions are just inverses of exponential functions, so they will share that special relationship as you will see as we go through this homework. So for number 1, for each of the functions given, determine A, the reference point, B, whether the function represents growth or decay, C, the 1 unit or 1 year change factor, and D, the 1 unit percent change. So let's take a look at this first one, and let's recall the general form of a logarithmic or of an exponential function, because these are all exponential functions, and that is y is equal to y sub 1 times b to the x minus x sub 1 power, where x sub 1 and y sub 1 is our reference point, b is our 1 unit change factor. Okay, so here it looks like our reference point is going to be 2, 28.4. And then whether the function represents growth or decay, remember if we keep multiplying by a number that's larger than 1 over and over and over again, that's going to grow. Likewise, if we multiply by a number less than 1 over and over and over again, it's going to decay. So our change factor is 1.37. So that's growing, so it's going to be a growth factor, or a growth function. C, our 1 unit or 1 year change factor, that's this value in here, and that's going to be 1.37. And then our 1 unit percent change, remember that's the percent change that we want, just how much it's changing by percentage-wise. So we're going to take off this 1 here, and this is going to be 37%. So take off the 1, convert it from a decimal to a percentage, and there we have it. So the second one, let's see here. Our reference point for the second one is going to be, well, there's nothing subtracted off of here from the x. There's no x1, or there is, but it's technically 0, so we're going to have 0, 19. And let's see, b, this is going to be a decay function because it is multiplied by a change factor that is less than 1. And then the 1 unit change factor, we see that we have this 0.77, but it's to the 3x. Well, really, if you recall our rules of exponents, we can actually rewrite this as 0.77 cubed. We can put the 3 on the inside of the parentheses. And so this is actually going to be our 1 unit change factor. And if we were to plug that into our calculator, or I suppose do it by hand if you really like, we get 0.4565. And then our 1 unit percent change, well, since this is decaying, we want to take the 1 and subtract this from it, and that will be our change factor. So, or sorry, not our change factor, it'll be our 1 unit percent change. And it's going to be a minus because we are going down, we're decaying. And it looks like, let's see, I just want to make sure I get the right numbers here, minus 54.35%. And then looking at this last one here, our reference point is going to be 1, 15.3. Well, actually, it's going to be negative 1, 15.3. Because remember, it's a minus x sub 1. This is plus, so it's going to be minus a minus. That's how we get the minus there. Let's see, this is going to be a growth function because we keep on multiplying by a number greater than 1. And then let's find our 1 unit change factor. Well, again, we can kind of play with the exponents here just a little bit, and we would get 1.8 to the 1 over 4th power because we're dividing our exponent by 4. So it's going to be 1 over 4. Plugging that into our calculator, we get 1.1583. And then for our percent change, it's just going to be we're going to get rid of this 1 here since it's the growth, and it's going to be 15.83. We want to put it into a percentage, so changing that from a 1, or in terms of a 1, to in terms of 100. So there we have it. Number 2, what is a log? And that is when you determine the log of a number, what are you finding? For example, explain what your answer to log base 3 of 100 represents. So let's see. Well, a log is essentially an exponent. And if we have this log base 3 of 100 here, we can actually switch it into a different form. And our general form here, I guess I'll write off to the side, is if we have some base value to an exponent and it equals something else, such as b to the x equals y, we can actually write that in a log form as log base our same b of y equals x. So notice what this is solved for. This log equals our x, it equals our exponent. So the log is just basically telling us, in this case, 3 to the power of what gives me 100. Maybe it'll make a little clearer if I were to write it into this into this exponential form. So we have 3 to the, let's see, be 3 to the y equals 100. So 3 to what power gives us 100? Well, we can kind of estimate here. 3 to the, well, I'll do it off to the side over here. 3 to the first power is 3. 3 squared is 9, and 3 cubed is 27. 3 to the fourth is 81, and 3 to the fifth is 243. So our y value here, our log base 3 of 100, should be somewhere between 4 and 5, because 3 to the fourth gives us 81, and 3 to the fifth gives us 243. So if we were to plug that into our calculator, just to make sure here we get the actual value, we'd want to go to hit math, and you can scroll up or down, but go to log base. Remember, it's going to be log base 3 of 100, and there we go. We get 4.19, which is in between 4 and 5. All right, so number 3, you read a news story about a bird whose habitat is threatened by human activity and pollution. Excuse me, 4 years ago, about 2,420 of the birds lived in the area, but today only 1,870 live in the area. Suppose the number of these birds living in the area follows an exponential model. How many years will it take before only 800 of these birds remain? Show all work. So first, we need to identify, or first we need to create a function that models this. Let's start off. I'll just label my t value. I'll be using t instead of an x here. It's going to be the number of years since, well, I guess since today. I should have said from today, but oh well. So number of years, it's going to bother me, from today. Okay. So first we need to find our 1 unit or change factor. Well, not 1 unit, but just our change factor here. So we're going to take 1870, and we're going to divide it by 2420. Because remember, we can take 2 consecutive outputs, divide them, and we can find our change factor. That's going to be 0.7727. So to create our function now, it's in this general form up here that I have. and let's see my screen. There we go. And so it's going to be y sub 1 times b to the x minus x sub 1. Well, here, this is going to be our base here. Our y sub 1, let's see, how many is alive today? So 1870. So our function is going to be y equals 1870 times our growth, or our change factor of 0.7727, and then to the t over 4th power. And it's over 4 because there were 4 years in between these two numbers. And so we want to take that into consideration, so we need to divide our exponent by 4. Well, now we want to know how many years will it take for only 800 of the birds to remain. Well, in this case, we're going to set our function equal to 800. We want to know when will our function of 1870 times 0.7727 to the t over 4th power, when will that equal 800? And so now we're tasked with this idea of solving for values here when working with exponential functions. And so when we're solving for them, we will definitely be using this idea here, going in between exponential form and logarithmic form. Okay, so in our quest to solve for t, that's what we're solving for in this case, we want to go ahead and divide both sides by this 1870. So what we have now is 800 divided by 1870. It's going to give us roughly 0.4278 is equal to, now this goes away, which is what we wanted, and we have 0.7727 to the t over 4th power. So from here, notice that we are now in something like this form, b to the x equals y. We have 0.7727 to the t over 4 equals 0.4278. So let's go ahead and put it into log form so we can solve for this exponent. So see what happens when we put it into log form. Log is solved for what was our exponent. So we can take this and we can put it as log base 0.7727 of 0.4278 is equal to t over 4. And then at this point, we can multiply both sides by 4, because we want to get t by itself, right? T is divided by 4, so we want to multiply both sides by 4, which will leave us with 4 times log base of 0.7727, 0.4278 is equal to t. And now we can just plug this into our calculator. So let's see here. 4, and then to get my log, I need to go to math, then go up to log base, because we need to be able to pick our own base here. 0.7727, 0.4278, and there we have it. T is equal to 13.17 years. So how many years will it take for only 800 of the birds to remain? 13.17 years. Awesome. Let's go on to page 2 now. Now it says algebraically solve each equation in exercises numbers 4 through 9. Then check your answer to show that it makes sense. So, I guess let's just get started doing it. So here what we can immediately do is we can put it into log form. So let's recall how this works. If we have b to the x is equal to y, then we can say x is equal to log base b of y. So let's go ahead and put this into log form. We'll solve for x. So this is log base 6 of 45 equals x. And so yeah, we just solved it algebraically. Let's put this into the calculator just to kind of see what we got going on here. So we have x is equal to 2.12. Now, to check our answers, we can kind of use what we did earlier to check our answers. We can think, okay, what does the different power of 6 give me? Well, let's see. I know that 6 squared is going to give me 45, or sorry, 6 squared is going to give me 36. And I know 6 cubed, let's probably have that memorized. There we go. This gives me 216. So it makes sense that our x fell between 2 and 3 because, well, 45 is between 36 and 216. All right, going on number 5 here. So we don't have it quite in this form just yet that I have here in the top left. We need to first divide both sides by 5 because we need that base by itself. So we're going to have 3 to the p is equal to, let's see, 12. And then now we can put it into log form. So we can say log base 3 of 12 equals p. And we can put that into our calculator. So p is roughly equal to 2.2619. Well, that should be a decimal there. Okay. Awesome. Let's just kind of go through this, do exactly what we did back here. So we have 3, let's see, 3 to the first, well, 3 to the second power gives me 9, and 3 to the third power, or 3 cubed, gives me 27. And it looks like, yes, 12 falls between 9 and 27, so our answer was 2.2619. That's between 2 and 3. We're good. Okay. Now take a look at this one. Again, we want to get that base by itself, so we need to divide both sides by 34.5 or 35.4. So let's see, just want to make sure I put that in right. Okay, so we have 5.5593 is equal to 1.65t. And now we can put it into that log form. So we can say log base 1.65 of 5.5593 is equal to t. And plugging that in to our calculator. Oh, I goofed. Let's see, 1.65, 5.5593. We get t is equal to roughly 3.556. Awesome. Okay. So let's see here. To check this, what we can do is we can actually plug this back into t, into our original equation, and see what we get. See if we get 196.8. So let's see, we have 35.4 times 1.65 to the 3.556 power. Ooh, something went wrong there. What did I do? Oh, I put this in wrong incorrectly. Sorry about that. So log, excuse me, log base 1.65 of 5.5593. There we go. That's the correct answer. 3.425 or 26. Okay. Now let's plug that one back into the original one and see what we get. 35.4 times 1.65 to the 3.426. And there we have it. We get very close to 196.8. So we check that one. Awesome. All right, going to number 7. This one we can just put right from the log form, or from the exponential form into log form. So we can say this is log, let's see, base 4.5, 92 equals x. Plugging that in, what do we get? And we get just barely over 3, so 3.01. Awesome. And let's plug that in. Let's see what 4.5 to 3.01 is, just to kind of verify what we're doing here. There you have it. We get very close to 92. The reason these are off is because we have to round, and so as long as they're very close, we should be good. And 92.5 is very close to just 92. Okay. Check that one. Now let's see here. Okay, here we want to divide both sides by 15. So we have 2 to the m is equal to, let's see, 57 divided by 15, 3.8. And, okay, let's put it into log form now. So log base 2 of 3.8 equals m. And let's see what that gives us. And m is equal to 1.926. So let's plug that into m here and see if we get something close to 57. And there we have it. Very close to 57. We're good. Okay, and then finally here, we need to divide both sides by 1.23. We want to get that base by itself. So that's going to give us 2.34 to the p is equal to whatever this mess is, 117.886. All right, then we could put into log form. So log base 2.34 of 117.886 is equal to p. And let's see here. Putting it into our calculator. We get p is roughly 5.61. So plugging that back in, let's see if we get something close to 145. There we have it, very close to 145. So we're good. Cool. All right, let's go on to some kind of real-world situations here that we can use for logarithms in. So, an initial amount of 80 milligrams of caffeine is metabolized in the body and decreases by 17% each year. Define a function to model this context. Be sure to define any necessary variables. So I'll use t again. So t is going to be the hours since taking caffeine. All right. So let's see here. This is going to be a pretty easy function to create. It's just going to be f of t is equal to 80 times 0.83 to the t power. We have to recall this is the y value of our reference point. Our only reference point is the initial reference point, which would mean our reference point would be 0, 80, because we, at 0 minutes or 0 hours, we take 80 milligrams. So that's where this 80 came from. This 0.83 is, I turned this into a decimal, so 0.17, subtracted it from 1, since it's decreasing, and I got 0.83 there. And then t minus 0, I don't need to write the minus 0. So that's our function here. B, how many hours will it take until only 13 milligrams of caffeine is left in the body? Well, now when you take this function and set it equal to 13. All right, so let's see here. We want to divide. So now this looks just like what we're doing up here, right? So it shouldn't be anything new. So we're going to divide both sides by 80. And 13 divided by 80 is going to give us 0.1625. And that's going to be equal to 8.3 to the t power. Okay. So now we can put it into log form. So we say log base 8.3 of 0.1625 equals t. And let's see what that gives us. Oh, I'm sorry, 0.83. I was wondering about that. 0.83. There we go. And t is going to give us, or t is going to be 9.75. So how many hours until only 13 milligrams of caffeine is left in the body? About 9.75 hours. Awesome. So let's move on to the next page now. All right, so number 11. The market for medical 3D printing is expected to grow to 1.21 billion by 2020 from about 660 million in 2016. Assuming exponential growth, write a function to model the situation, clearly define any variables. So let's see. I'm going to make t the years since 2016. And let's see. I need to find my my growth factor. But to do so, I need to divide my 2 points here, my 2 outputs. But we want to make sure that they're in the same kind of number, if you will. This is in terms of billions, so 1.21 billion. This is in terms of millions. So let's put this millions into billions. So let's just note that 660 million will equal 0.66 billion. So we're going to set up this equation in terms of billions, okay? So I'm going to take, let's see, to find my growth factor, I'm going to take 1.21 divided by 0.66. And that's going to give me 1.833. So my function here is going to be, let's see, we're going to have f of t is equal to our reference point. So I'm going to pick the reference point from in 2016. So 0.66 times 1.833 to the t over 4 because this is actually between 4 years, right? Between 2016 and 2020. So that's why I need to divide that by 4. All right, use the function to estimate when medical 3D printing will reach 10 billion. So solve algebraically. Okay. So because I have this set up in terms of billions, 10 billion would just be 10. So 10 equals 0.66. 1.833 to the t over 4 power. So I just want to know when we will get to $10 billion. So to solve for this, we need to get rid of that 0.66. We want to get the base by itself, so we can then put it into log form. This will give us roughly 15.15 is equal to 1.833 to the t over 4. We can convert this to log form now. So log base 1.833 of 15.15 equals t over 4. Now, to finish off for t, we need to multiply both sides by 4. So we get 4 log base 1833 15.15 equals t. Putting that to our calculator. We get t is roughly 17.94. So, when will it reach 10 billion? In about, well, we could say about 18 years. 17.94 is close enough to 18. All right. So number 12, suppose you know that the population of deer is increasing exponentially at a rate of 24% every 3 years. A, by what percent will the population increase in 8 years, in 30 years, in 2 years? So let's first think about what the 3-year change factor is. So it's increasing at a rate of 24% every 3 years. So the 3-year change factor is going to be 1.24. Looking for 8 years, it'll be 1.24 to the 8 over 3 power. Now, you might be wondering, how is it 8 over 3? Well, this first one is 3-year change factor. So it's essentially like saying 3 over 3, because it takes 3 years for that change factor to happen, and it's over 3 years, period. So that's why it's 3 to the 3, or 3 divided by 3 is just 1. But that's why we need to put 8, because this change factor happens over 3 years, but we want to know what is the change factor in 8 years. Okay? So the 30-year change factor is going to work the same way, 1.24, but this is going to be 30 over 3. And then the 2-year change factor is just going to be 2 over 3. So now it's asking, well, really the question is asking by what percent will the population increase? So we need to find the percentage of all of these. So let's see, 1.24 to the 8 over 3 power, and that's 1.7747. So this is really an 8-year percent increase of 77.47%. 77.47 is increasing, and I just subtracted the 1 from it. Okay. This next one, let's see, 1.24. 24. I'm goofed. Okay, 1.24 to the 30 over 3, and that's going to be 800 or 8.5944. So a 30-year percent increase, I'm going to have to do the same thing to get the percent. I just need to subtract 1 from it, and that's going to be 759%. 0.44%. Okay. Again, I'm just subtracting 1 from these. And then, here, 1.24 to the 2/3 power. That's 1.1542. So it's a 2-year percent increase of roughly 15.42%. Awesome. Now, how long will it take for the population to double? Well, this is kind of interesting. So we don't really have a reference point, do we? We don't know what the population is starting at, but we do have a multiplicative comparison here, 1 to 2, right? So I can write this as just our change factor, and then that will be what, to the t over 3 power, because it's every 3 years, and I can set that equal to 2. This is like saying my initial population is 1, and I want to know when it will get to 2, or whatever it is now. When will it essentially double? So I don't really need that, but we can go ahead and put this into log form. So I can say log base 1.242 is equal to t over 3, and then solve for t. So we can just multiply both sides by 3. We have 3 log base 1.242 equals t. Let's see. And we get 9.667. So t is equal to 9.667. So the population will double every 9.667 years. Awesome. All right, on to the last page. Okay, so suppose you have an initial mass of bacteria of 8 micrograms, which increases by 17% every 3 hours. What is the doubling time of this bacteria? So let's see. Let's define my t here. So hours since initial mass. Okay. So our function here, well, again, we're just looking for the doubling time. So I don't need to worry about this 8 micrograms. I could set it up as my function and set it equal to 16, but I could just do what we did on the last example and think, okay, well, what is my change factor? My change factor is going to be 1.17 if it's increasing by 17% every 3 hours. Well, 1.17 to the 1/3 power, technically, because every 3 hours. So I can say this. I can say 1.17 to the t over 3 power is equal to 2. So I want to know when will my change factor double to 2? So, or how many times do I need to multiply by the change factor, rather, in order for the population to double? Okay. So here we can put it into log form. Log 0.1772 equals t over 3, and then multiply both sides by 3. So let's see what this is. 3 log, oh, did something. There we go. 3 log 1.17 All right. So t is equal to roughly 13.245. So I guess it. So the doubling time is roughly or about 13.245, and it's hours. Oh, not years. I just said hours. Hours. There we go. Awesome. Okay. B, algebraically determine how many hours it will take for the mass of the bacteria to decrease by 63%, or to increase by 63%. So now I can take this function, not set it equal to 2, because that would be doubling, right? But I can take the 1.17 t over 3 power. And let's see, an increase of 63%, would it make sense if I wrote this as 1.63? I want to know when my initial mass of bacteria will get to the 63%. So we do the same thing, put in the log form. And then multiply both sides by 3, which will give us 3 log base 1.17, 1.63 equals t. Plugging that in, we get t is equal to 9.336. Awesome. So I can say every 9.336 hours, the mass grows by 63%. Awesome. Okay, last question here. Suppose you have an initial mass of bacteria of 58 micrograms, which decreases by 12% every 2 hours. What is the half-life of this bacteria? So let's first find our change factor here. And our change factor is going to be, well, we're going to take 1 and we're going to convert this 12 to a decimal, so 0.12, and we're going to subtract it from 1. So our change factor is going to be 0.88, and it's every 2 years, so we're going to have to divide our t by 2 here. This would be our 2-year change factor. So let's see here. 0.88 to the t over 2, that's how much it's changing by. We want to know what is the half-life. So when will this 1 be equal to 0.5? Okay. And again, I don't really need this 1 here. So let's convert this into log form. And let's see here. So log form, oh, my computer, there we go. All right, so log form here is going to be log base 0.88 to 0.5 is equal to t over 2. Multiply both sides by 2 now. So we have 2 log 0.88, 0.5 is equal to t. And we get t is equal to 10.845. Okay, so the half-life is 10.845, and what is the hours? Okay. And then how long will it take for the mass of bacteria to be 25 micrograms? Well, in this case, we will need our initial amount of 58. So I want to know, I have 58 now, and it's decaying. Now I want to know when it's going to equal 25 micrograms. So we can go ahead and divide both sides by 58. We have 0.88 to the t over 2 power is equal to roughly 0.431, and then put it into log form. Again, multiply by 2 because we're solving for t. So we have t is equal to, let's put this in the calculator. Let's see, so t is equal to 13.168. So how long will it take? It will take, let's see, 13.168 hours. Awesome. So that is Module 8 homework. I hope this video helped, and have a good day.